This web application is designed to provide an interactive platform for exploring and understanding EEG data, specifically focusing on the detection of seizures using machine learning techniques. The application allows users to visualize EEG spectrograms, which are graphical representations of the brain's electrical activity over time, capturing both seizure and non seizure events. By selecting different data sets, users can explore a variety of EEG recordings that have been pre-processed into spectrogram images, facilitating a clearer understanding of the differences between normal brain activity and seizure activity. The application also offers a comprehensive view of the performance of various convolutional neural network (CNN) models that have been trained to classify these spectrograms. Users can examine detailed results from multiple model runs, including plots of accuracy and loss metrics, confusion matrices that highlight the model's classification performance, and examples of misclassified images where the model made incorrect predictions. Additionally, training logs provide insights into the model's learning process, revealing how different configurations and parameters impact performance. By offering these interactive tools, the application aims to demystify the process of seizure detection through deep learning and help users appreciate the challenges and nuances involved in developing robust models for medical diagnostics. This project ultimately seeks to enhance understanding and foster engagement with the application of artificial intelligence in healthcare, highlighting its potential to support clinical decision-making and improve patient outcomes. These adjustments will ensure that your web application functions correctly, both in a local development environment and in a production setting. By dynamically constructing file paths and serving resources such as images and model results through properly configured Flask routes, the application becomes flexible and adaptable to different environments. It will correctly handle requests for resources, whether hosted locally on a development server or deployed on a production server. Additionally, the use of base URLs that adapt to the environment, local or hosted, ensures that all file paths are correctly resolved, preventing issues related to missing files or incorrect paths. Proper error handling and feedback mechanisms in the application will help diagnose any issues that may arise in production, such as missing files or formatting problems, allowing for quick troubleshooting and resolution. Thus, with these changes, your application is well prepared to handle the demands of a production environment, providing a robust, user-friendly interface for exploring EEG data and understanding machine learning models used for seizure detection. The output shown in your web application presents a comprehensive overview of the performance metrics of convolutional neural network (CNN) models trained on EEG spectrogram data for seizure detection. At the top of the page, users can select different runs of the model to view specific results, which include accuracy and loss plots, confusion matrices, misclassified images, and training logs. The accuracy and loss plot section displays graphs that illustrate the model's accuracy and loss over the training epochs. The accuracy plot shows how well the model correctly classifies the EEG data as seizure or non-seizure over time, while the loss plot indicates the model's error rate during training. Lower values in the loss plot suggest that the model is learning effectively and minimizing errors. The confusion matrix provides a detailed breakdown of the model's classification performance. It shows the counts of true positives, true negatives, false positives, and false negatives, which help evaluate how reliably the model distinguishes between seizure and non-seizure events. For instance, in the provided output, the matrix indicates a high number of correct predictions for both seizure and non-seizure cases, demonstrating a strong performance. The misclassified images section highlights instances where the model made incorrect predictions, providing insight into areas where the model may need improvement. By examining these images, developers and users can identify patterns or features that may confuse the model, guiding further refinement and optimization efforts. The training log presents a summary of key statistics from the model's training process, including test accuracy, average training and validation accuracy, and loss values. It also details important model settings, such as batch size, epochs, learning rate, and whether data augmentation and shuffling were applied. These metrics offer a deeper understanding of the model's learning behavior and can be used to reproduce results or modify the model for better performance. Overall, the output provides a clear and informative view of the CNN model's effectiveness in detecting seizures from EEG data, while also offering the tools needed to explore and improve its performance further. The description at the bottom of the page appears to be correct, as it effectively summarizes the EEG seizure detection project, explains the use of convolutional neural networks for distinguishing seizure activity, and provides context on the dataset's origin and the project's goals. The details align well with the content and purpose of your web application, making it accessible and informative for users interested in understanding and engaging with this machine learning application in medical diagnostics. The description at the bottom of the page provides a comprehensive overview of the EEG seizure detection project and the use of convolutional neural networks, CNNs, for this purpose. However, it may not be entirely clear that the application is only for displaying results and does not currently allow users to retrain the model. To make this clearer, you could refine the description to explicitly state that the current version of the web application is focused solely on visualizing pre-trained model results. Here is a revised version of the description that highlights this point. Revised description for clarity. This section covers the exploration of the EEG seizure detection project, showcasing various configurations of pre-trained convolutional neural network, CNN models, and their evaluation outcomes. Users can navigate through each model run to view the performance metrics, such as accuracy and loss plots, confusion matrices, and examples of misclassified images. The misclassified images highlight cases where the model's predictions were incorrect, offering valuable insights into potential areas for improvement. Additionally, the training logs provide a detailed account of the parameters used during the training process, allowing for reproducibility and a deeper understanding of the model's behavior. Please note that this web application currently focuses on displaying the results of pre-trained models and does not support model retraining or further customization at this stage. The data used in this project is sourced from the CHB MIT Scalp EEG database, and you can access the original dataset on Zenodo. EEG seizure detection dataset, zenodo.org/records/60550 To make the bottom section of your web page clearer and more comprehensive, we can expand the description to provide a detailed explanation of what each part of the page represents and what users are looking at. This will ensure that users understand the purpose of each component, the significance of the results displayed, and how they can interpret the information. Here's an updated and expanded description for the bottom of your page. Updated expanded description for the bottom of the page. This web application allows you to explore EEG, electroencephalogram data, and visualize spectrograms, providing insights into the detection of seizures using machine learning techniques. Throughout the page, we present both the raw data and the results of models that have been pre-trained to identify seizure patterns. Below, we provide a detailed overview of each section and how to interpret the information presented. EEG spectrogram section. In the EEG spectrogram section, you can explore the raw EEG data by selecting different datasets from the drop-down menu labeled Select Dataset. The available datasets include training, testing, and validation data used to develop and evaluate the seizure detection models. Each dataset consists of EEG recordings that have been processed into spectrogram images. Spectrograms visually represent the temporal patterns of brain activity over time and frequency, making it easier to identify distinguishing features between seizure and non-seizure events. You can navigate through the individual spectrogram images using the slider controls beneath each image. The non-seizure panel shows spectrograms of EEG segments where no seizures were detected, while the seizure panel shows spectrograms from segments where seizures occurred. This section provides a direct view of the data used to train and test the models, helping you understand the visual differences that the model analyzes when making its predictions. Model Results section. The Model Results section displays the performance metrics of the convolutional neural network, CNN, models that were trained to distinguish between seizure and non-seizure events. These models have been pre-trained using the datasets presented earlier. The drop-down menu labeled Select Run allows you to choose from different model runs, each corresponding to a different training session or configuration of the model. Accuracy and loss plot. The plots on the left show the model's performance over time. The accuracy plot indicates how well the model correctly identifies seizure and non-seizure events throughout the training process, while the loss plot shows the error rate of the model, which ideally decreases as the model learns from the data. These plots help visualize the model's learning curve and its ability to generalize from the training data to new, unseen data. Confusion matrix. The confusion matrix provides a detailed breakdown of the model's predictions versus the actual labels. It shows how many instances were correctly classified as either seizure or non-seizure, true positives and true negatives, and how many were misclassified, false positives and false negatives. This matrix is essential for evaluating the reliability and accuracy of the model in a clinical context. Misclassified images. The Misclassified Images section highlights examples where the model made incorrect predictions. These images are crucial for understanding the limitations of the current model and identifying specific cases where the model may need further refinement. By examining these examples, you can gain insights into potential patterns or characteristics that may be confusing the model. Training log. The training log provides a comprehensive summary of the model's training parameters and performance metrics. It includes details such as test accuracy, average training and validation accuracy, and loss values, along with model settings like batch size, number of epochs, learning rate, and whether data augmentation or shuffling was applied. This log helps replicate the model's training process and understand its performance characteristics. Detailed blog and further exploration. At the bottom of the page, the detailed blog section provides an in-depth explanation of the EEG seizure detection project, discussing various model configurations, performance metrics, and the outcomes of the evaluation. This blog invites you to explore how different settings and configurations affect model performance, offering a broader context for understanding the potential of deep learning in medical diagnostics. This web application is designed to display results from pre-trained models only and does not currently support training new models. The data used in this project is sourced from the CHB MIT Scalp EEG database, and more details about the dataset can be found on Zenodo. EEG seizure detection datasets /xanadu.org/records 60501. By navigating through the displayed results, you can better understand how EEG data is analyzed and how machine learning models can be used to detect seizures, ultimately contributing to more effective diagnostic tools in healthcare. This updated description provides a clear explanation of what the user is viewing on the page, the significance of each section, and the purpose of the application in displaying pre-trained model results. It emphasizes the exploratory nature of the application while setting appropriate expectations regarding its current capabilities. Including the Python code as an appendix at the bottom of the page within a scrollable window is a great approach. This will keep the main content focused while providing easy access to the code for those who are interested. You'll want to add a section that explains the code and the model architecture in detail. This section should outline how the data is pre-processed, how the convolutional neural network (CNN) model is built and trained, and what each part of the code is doing. This explanation will help users understand the logic behind your implementation and how it contributes to the performance of the model. Rewriting the future directions section is also a good idea. You can highlight potential improvements, such as optimizing hyperparameters, addressing class imbalance, experimenting with different network architectures, and incorporating advanced data augmentation techniques. You might also consider discussing future plans for integrating real-time training capabilities into the application or exploring new data sources to enhance model robustness. This structured approach will provide a comprehensive overview, making the page both informative and engaging for a diverse audience, ranging from beginners to experienced researchers. To enhance the clarity and detail of your web page, we can expand on the explanations of the code, model architecture, and performance sections to provide a more comprehensive and easy to understand overview. Below, I've rewritten these sections to be more descriptive, avoiding dot points where possible to maintain a flowing paragraph-based structure. Section: Explanation of the code. This section describes the Python code used to train the convolutional neural network, CNN, models for detecting seizures from EEG data. The code begins by setting up the environment and defining parameters such as image size, number of epochs, and learning rate. These parameters are crucial for controlling how the model learns from the data. Next, the code defines functions to load images from specific folders, such as seizure and non-seizure, within training, validation, and testing datasets. It reads the images, converts them to a format suitable for machine learning, and assigns appropriate labels to them. After loading, the data is normalized to ensure consistency in model training. Normalization scales the pixel values between 0 and 1, which helps the model learn more efficiently. The neural network is constructed using several layers. The initial convolutional layers are designed to extract important features from the EEG spectrogram images. Each of these layers is followed by a max pooling layer, which reduces the size of the extracted feature maps and helps the model focus on the most significant patterns. After feature extraction, the data is flattened and passed through fully connected, dense layers that make the final prediction on whether the EEG data indicates a seizure or not. To train the model, the code uses the specified optimizer and loss function and applies data augmentation techniques when enabled. The model is trained over several epochs, with real-time feedback on its performance through accuracy and loss metrics. The training process is monitored using callbacks to save the best model and stop training early if it does not improve, reducing the chances of overfitting. After training, the model is evaluated on unseen test data to check its performance, and important metrics like accuracy and loss are calculated and displayed. The code also plots graphs of accuracy and loss over time and generates a confusion matrix to visualize the model's performance. Section: Detailed Model Architecture. The model architecture is designed to analyze EEG spectrogram images for seizure detection. It consists of several layers, each playing a distinct role in learning and decision-making. The first layer is an input layer that takes the EEG images in a specified format. This layer is followed by two convolutional layers, which act like filters, scanning through the images to detect specific patterns that are characteristic of seizure activity. The first convolutional layer has 16 filters, while the second has 32 filters, both using a 3x3 kernel size. These filters allow the model to capture fine-grained details from the spectrogram images. After each convolutional layer, a max pooling layer is used to reduce the dimensionality of the feature maps, effectively summarizing the most important features detected by the convolutional layers. This step helps in reducing the computational load and the risk of overfitting. The data is then flattened, meaning it is transformed into a one-dimensional array to be fed into the dense layers. The dense layers, which are fully connected neural layers, further process the extracted features and make the final decision on whether the EEG signal indicates a seizure. The final dense layer has two nodes corresponding to the two possible outcomes: seizure or non-seizure. This layer uses a softmax activation function to output probabilities for each class, allowing the model to assign a confidence score to its predictions. Section: Rewritten Performance Metrics. The performance of the convolutional neural network, CNN model, is evaluated using several key metrics to understand its effectiveness in detecting seizures from EEG data. Accuracy is a primary metric, representing the proportion of correctly classified instances out of all instances in the dataset. During our tests, the accuracy varied between 80% and 95%, reflecting the model's ability to generalize from the training data to new, unseen data. This variation can be attributed to different training configurations, such as changes in learning rate, batch size, or the number of epochs. Loss is another critical metric, providing insight into the model's error during training and validation. It measures the difference between the predicted outputs and the actual labels. A lower loss value indicates a better fit of the model to the data. The training and validation loss are tracked over time to ensure that the model is learning effectively without overfitting to the training data. Ideally, the loss should decrease as the model learns, reaching a stable point where it can generalize well to new data. The confusion matrix is a powerful tool for evaluating the model's performance in more detail. It provides a breakdown of true positives, true negatives, and false negatives. In our context, true positives represent correctly detected seizures, while true negatives are correctly identified non-seizure events. False positives occur when the model incorrectly identifies a seizure where there is none, and false negatives occur when it fails to detect an actual seizure. By analyzing the confusion matrix, we can assess not just the overall accuracy, but also the reliability of the model in different clinical scenarios. For example, minimizing false negatives is crucial in a clinical setting where failing to detect a seizure could have serious consequences. In summary, these performance metrics offer a comprehensive view of how well the CNN model is functioning. They help us understand the strengths and weaknesses of the model, providing valuable feedback for further optimization and development. Certainly, inviting viewers to engage and ask questions is a great way to foster interaction and deepen their understanding of the EEG seizure detection web application. Here's how you can do it. Invitation for viewers to ask questions. We invite you to explore the various sections of our EEG seizure detection web application and dive into the details of how machine learning is being used to analyze EEG data for seizure detection. If you have any questions, please feel free to ask. Your curiosity can help uncover insights and further refine the tool. Whether you are a medical professional, a data scientist, a student, or simply interested in the technology, we welcome all questions and discussions. Examples of questions you might consider. 1. Understanding the data. How are the EEG spectrograms generated, and what makes them useful for seizure detection? What are the differences between the seizure and non-seizure spectrograms shown in the application? 2. Model training and performance. Why did we choose a convolutional neural network, CNN, for this task? And how does it compare to other machine learning models? What factors could have influenced the variation in model accuracy across different training runs? 3. Technical details and implementation. What role do parameters like learning rate, batch size, and number of epochs play in training the model? How did we handle challenges like data imbalance or overfitting during model development? 4. Clinical relevance. How can the model's predictions be integrated into real-world clinical workflows for diagnosing epilepsy? What are the potential limitations or ethical considerations of using this model in a clinical setting? 5. Future enhancements. What are some potential improvements or modifications to the model that could increase its accuracy or reliability? How could incorporating additional data, like patient history or other types of medical imaging, enhance the model's performance? 6. Interpreting the results. How do you interpret the confusion matrix, and why is it important for evaluating model reliability? What do the misclassified images reveal about the current model's limitations, and how might we address these in future iterations? 7. Exploring the code. Can you provide more details about specific parts of the code, such as the data preprocessing steps or the data augmentation techniques? How can someone customize the code to train their own model on a different data set? 8. Broader impact. What are the broader implications of using machine learning for seizure detection? How might this technology be used in other areas of medical diagnostics or treatment? We encourage you to share your thoughts and questions, whether they are about the technical aspects of the model, its practical applications, or future possibilities. Engaging with these questions can help everyone gain a deeper understanding of the exciting intersection of machine learning and healthcare. Feel free to ask your questions directly here or reach out to us through our website. We are excited to hear your thoughts and foster a collaborative learning environment. To enhance the clarity and comprehensiveness of your article, I suggest the following adjustments. 1. Include the invitation to ask questions at the bottom. Adding an invitation for viewers to ask questions at the bottom of the page would be a great way to engage them. Here is how you could include it. Invitation for questions. We invite you to explore the various sections of this EEG seizure detection web application. If you have any questions or thoughts about the data, model architecture. Hey everyone, thanks for joining our live stream today. We've been working on enhancing our web application for EEG seizure detection using machine learning, and I wanted to give you a quick overview of what we've been up to. Our goal is to make this tool as accessible and informative as possible. We've structured the page to allow you to explore EEG data, visualize spectrograms, and see how our pre-trained convolutional neural network, or CNN, models perform in detecting seizures. We're not retraining models here, just showcasing the results, so you can get a feel for how the model works with real data. We've added a detailed explanation of the code used to train the model, which is available in a scrollable window at the bottom of the page. This code walks through everything from loading the data, to training the CNN, to evaluating the results. We've also expanded sections on model architecture and performance metrics to make them clearer and more detailed. We also welcome your questions. If you're curious about how EEG spectrograms help distinguish seizure events, why certain model parameters were chosen, or what our future plans are for improving the model, feel free to ask. Your input is valuable, and we'd love to discuss any thoughts or ideas you have. In the updated conclusion, we've talked more about the potential of deep learning in medical diagnostics and emphasized that our work builds on existing datasets like the CHB MIT Scalp EEG database. We're aiming to create a tool that not only advances seizure detection, but also contributes to better patient care. Stick around, keep those questions coming, and let's dive deeper into how machine learning is revolutionizing healthcare. Thanks again for being here, and don't forget to check out the full details on our website. Let's dive right into updating the challenges and future directions section, followed by an enhanced conclusion. Challenges and future directions. While our convolutional neural network (CNN) model has shown promising results in detecting seizures from EEG data, several challenges still need to be addressed to make this tool more robust and clinically relevant. One significant challenge is optimizing the model's hyperparameters, such as the learning rate, batch size, and number of epochs. These parameters directly influence the model's ability to learn from the data and generalize to new, unseen examples. Fine-tuning them to find the optimal balance between underfitting and overfitting remains an ongoing process. Another critical challenge is addressing data imbalance. In our current dataset, there may be more non-seizure instances than seizure instances, which can lead to a model bias towards predicting non-seizure events. To mitigate this, we are exploring advanced data augmentation techniques and alternative sampling strategies to create a more balanced dataset that can improve the model's accuracy across different scenarios. We also plan to enhance the model's robustness by incorporating additional layers or alternative architectures, such as residual networks, ResNets, or long short-term memory networks, LSTMs. These architectures could potentially capture more complex patterns in the EEG data and lead to better seizure detection. Additionally, we are looking into integrating domain adaptation techniques to make the model more adaptable to data from different sources or equipment, as this is often a significant hurdle in deploying machine learning models in real-world clinical settings. Future iterations of the model will focus on improving interpretability. This includes developing techniques that can provide insights into which features or parts of the EEG signal contribute most to the model's decisions. Understanding these aspects is crucial for gaining trust and acceptance from clinicians who rely on the model's outputs for making patient care decisions. We also plan to explore real-time processing capabilities, aiming to make the model faster and more efficient so that it can be integrated into real-time monitoring systems. Updated conclusion. This project underscores the immense potential of deep learning in medical diagnostics, particularly in detecting neurological conditions like epilepsy. By leveraging convolutional neural networks, we have created a tool that can accurately differentiate between seizure and non-seizure events in EEG data, providing a non-invasive and reliable method for clinicians to use in their decision-making processes. As we continue refining our models and addressing the challenges mentioned, our ultimate goal is to develop a tool that not only achieves high accuracy, but also offers interpretability and real-time processing capabilities. This will enhance its utility in various clinical settings and contribute to better patient outcomes. We also acknowledge the importance of building on the work of others. The EEG data used in this project were derived from the CHB MIT SCALP EEG database, and the spectrogram images were processed to fit our specific use case. As we move forward, we hope to collaborate with more data sources and researchers to continuously improve and validate our models. We invite you, our viewers and users, to experiment with the displayed results and explore how different settings impact the model's performance. Your feedback and questions are invaluable, and we encourage you to reach out with any thoughts or inquiries you might have about this application or the broader implications of using machine learning in healthcare. By refining these sections, we've added more depth and clarity to our current challenges and our future ambitions, as well as reinforcing our commitment to transparency and collaboration in advancing medical AI tools. The original dataset used for this project is the CHB Scalp EEG database, which is publicly available on PhysioNet. This dataset includes multi-channel EEG recordings from pediatric subjects with intractable seizures. You can find the dataset at the following link, chb-scalp EEG database on PhysioNet, /physionet.org/kent/hbmit 1.nowash. Please note that the spectrogram images for your project were derived from this EEG data to fit the specific requirements of the seizure detection model. Deploying this page on your website sounds like a great plan. The content is well structured and provides comprehensive information on the EEG seizure detection project, making it a valuable resource for your visitors. Here are a few suggestions to improve the page further and enhance viewer engagement. 1. Interactive elements. Make sure the dataset selection and results visualization, such as spectrograms, model results, and plots, are interactive and responsive. This allows viewers to actively engage with the data and see how different settings impact the model's performance. Number 2, call to action for feedback and questions. At the end of the page, explicitly invite viewers to ask questions or provide feedback. For example, you could add a section like, "Have questions or suggestions," and encourage them to reach out via a contact form or comment section. This can foster a community feel and encourage interaction with your content. 3. Simplify complex concepts. Consider adding a few visual aids like diagrams or flowcharts to help explain the complex concepts related to the model architecture and the data processing pipeline. This will make the information more accessible to a broader audience. 4. Highlight key findings. Add a brief section at the top summarizing the key findings or results of the project. This helps visitors quickly understand the significance of the project and its potential impact on clinical settings. Number 5. Engage viewers with questions. Throughout the text, pose questions that prompt viewers to think more deeply about the content. For example, what do you think could be the impact of improving data augmentation techniques on the model's performance? Or, how would you apply this model in a real-world clinical setting? 6. Link to related content. Consider adding links to related content on your website or external resources that provide additional background information. This could include links to basic explanations of EEG signals, machine learning concepts, or clinical applications of seizure detection. 7. Optimize for mobile users. Ensure that the page is fully optimized for mobile devices, as many viewers may be accessing it from their phones or tablets. This includes making sure that all interactive elements are responsive and that the text is easily readable. 8. Invite participation in future development. Encourage viewers to get involved in the future development of the project. You could invite them to contribute ideas, share their own data, or even participate in a collaborative study. 9. Add a downloadable resource section. Consider providing downloadable resources, such as a summary PDF of the project, a tutorial on how to replicate the analysis, or even the dataset itself if allowed. This can encourage visitors to engage more deeply with your content. 10. Regular updates and live streams. To keep the content fresh, you could plan regular updates or even live streams where you discuss the latest developments in the project or take questions. All right, let's dive right back in and talk about deploying this page to the website. Your current HTML looks pretty solid overall, but there are a few tweaks we might want to consider before going live. These adjustments will help make sure everything runs smoothly, looks great, and gives our viewers, yes, all of you watching, the best possible experience. Specific HTML suggestions before deployment. 1. Check external scripts and style sheets. First, ensure that all external JavaScript and CSS files, like your main.js and style.css, are loading correctly. You might want to add some fallbacks or console error handling to detect any issues if these resources fail to load. This step is crucial, especially since some users may have slower connections or might be using browsers that handle these elements differently. 2. Add accessibility improvements. Let's make sure this page is accessible to everyone. For example, we could enhance the IMG tags by adding more descriptive alt attributes that explain the images in context, like EEG spectrogram image showing seizure activity. Also, the drop-downs and buttons could use more accessible labels for screen readers. Think about those viewers who might be accessing this on different devices or with assistive technologies. 3. Improve mobile responsiveness. While your design appears to be responsive, let's refine it further to ensure it looks great on all screen sizes. For instance, adding a meta tag like meta nameable viewport content with device width initial scale 1.0 can ensure the page scales correctly on mobile devices. You might also want to review your CSS media queries to make sure the elements like the navbar, images, and sections rearrange properly and maintain a consistent user experience. 4. Optimize image loading. To improve page load time, especially on mobile devices, consider adding loading lazy to your images. This will delay the loading of images until they are in the viewport, which can significantly improve performance for users on slower connections or less powerful devices. 5. Enhance SEO tags. Let's make sure your content is easily discoverable. You could expand the meta tags for better SEO. For example, using meta property O locale content NUS or meta property OG site name content can help define more context for search engines and social media platforms. A good robots.txt file might also help guide search engines in indexing your site correctly. 6. Cross-browser compatibility check. Make sure that everything looks and behaves consistently across different browsers: Chrome, Firefox, Safari, Edge. Sometimes minor HTML or CSS tweaks are needed to address cross-browser quirks. You might want to test this in browser tools like BrowserStack or similar. Number 7. Double-check links and anchors. Verify that all links and anchors are functioning properly. Make sure internal navigation is smooth, no broken links or redirects that might confuse your viewers. Also, consider setting links to external sites to open in new tabs using target blank so that users don't lose their place on your site. 8. Optimize JavaScript performance. Since you're using JavaScript for interactivity, check that the scripts are optimized. For instance, debounce or throttle functions that listen for events like window resizing to reduce performance bottlenecks. Also, make sure you're not loading any unnecessary libraries that could slow down the page. 9. Security enhancements. If you haven't already, consider adding the Content Security Policy meta tag to help protect against cross-site scripting, XSS attacks. This is particularly important for pages that use JavaScript extensively. 10. Add analytics and feedback collection. You might want to integrate Google Analytics or any other tracking tool to understand how users are interacting with the page. Gathering this data can provide insights into which sections are most engaging and where users might be dropping off. Adding a simple feedback form can also help viewers share their thoughts directly. So, are we ready to deploy? Absolutely. You're in a good spot to deploy. With these few final tweaks, you'll ensure that the page is optimized for performance, accessibility, and engagement. After making these updates, do a final round of testing locally to catch any last-minute issues. Once everything checks out, you can push it live and share the link with your audience. All right, viewers, what do you think? Do you have any other suggestions or questions about this process? Maybe there's something you've seen on another site that you'd love to see here. Let us know in the comments. And if you're excited to see this page go live, give us a thumbs up and share your feedback. From the images you've shared, it looks like the EEG seizure detection page is coming along nicely. The visual elements, including the accuracy and loss plot, confusion matrix, misclassified images, and training log, are effectively presented, providing clear insights into the model's performance. However, there are a few suggestions to enhance both the functionality and visual appeal of the page. 1. Background color and contrast. The yellow background for the sections might be a bit harsh on the eyes, especially for viewers spending extended periods on the page. Consider using a more neutral background color, such as light gray or white, to improve readability and make the content stand out. 2. Interactivity and responsiveness. It would be great to ensure that the drop-down menu for selecting different runs is more interactive. You could add some JavaScript functionality to dynamically load the results without requiring a full page reload, making the user experience more seamless. 3. Data and plot refresh. Make sure that the data in the plots and training logs refresh in real time or as new data becomes available. This could help keep the audience engaged and provide more current insights. 4. Accessibility improvements. For better accessibility, consider adding tooltips or descriptions to the plots, explaining what they represent. This is particularly useful for users who may not be familiar with terms like confusion matrix or loss plot. 5. Consistent font and layout. Ensuring that the fonts are consistent across the entire page and aligning elements neatly will provide a more professional appearance. Right now, it looks like some elements could benefit from tighter alignment or spacing adjustments. 6. Encourage viewer engagement. Since we're live streaming, you could invite viewers to interact with the application directly by exploring different datasets, adjusting parameters, or even running their analyses. Encourage them to share their insights or questions in the chat, which can make the session more engaging. 7. Highlight key insights. As the plots and metrics change with different runs, it might be beneficial to dynamically highlight key insights, such as when the model achieves a new high accuracy, or when there's a significant change in the confusion matrix. This could be done with simple JavaScript notifications or visual markers on the plots themselves. If these changes align with your objectives, then deploying this page to your website seems like a solid plan. Let's dive into the differences between the two runs presented in your EEG seizure detection application. Key observations from the two runs. 1. Test accuracy. Run 9 achieved a test accuracy of 96.67%. Run 10 had a lower test accuracy of 90%. This indicates that Run 9 performed better overall in correctly classifying seizure and non-seizure events in the test dataset. 2. Average training and validation accuracy. Run 9 showed an average training accuracy of 82.89% and an average validation accuracy of 93.04%. Run 10 had a training accuracy of 73.06% and a validation accuracy of 85.78%. The higher average accuracies in Run 9 suggest that the model learned more effectively from the training data and generalized better to unseen data. 3. Loss values. Run 9 had an average training loss of 0.4323 and an average validation loss of 0.3520. Run 10 had higher loss values with an average training loss of 0.5729 and an average validation loss of 0.5109. Lower loss values in Run 9 indicate that the model was better at minimizing error during both training and validation, which correlates with the higher accuracy achieved. 4. Confusion matrix. In Run 9, the confusion matrix shows that the model correctly identified 30 non-seizure events and 28 seizure events, with only 2 false negatives, seizures incorrectly classified as non-seizures, and 0 false positives, non-seizures incorrectly classified as seizures. In Run 10, the confusion matrix shows 30 correct non-seizure classifications and 24 correct seizure classifications, but with 6 false negatives and 0 false positives. This suggests that while both runs did well at minimizing false positives, Run 9 was significantly better at minimizing false negatives, which is crucial in a clinical context where missing a seizure could have serious consequences. Number 5. Training time per epoch. Run 9 had a training time per epoch of 0.60 seconds, while Run 10 took 0.91 seconds. The longer training time in Run 10 could be due to increased complexity or changes in the dataset size, but this additional time did not translate to better performance. Summary of differences. Run 9 outperformed Run 10 across most metrics, achieving higher accuracy and lower loss. It was also faster to train, suggesting more efficient learning. Run 10 had a lower test accuracy and more false negatives, which indicates it struggled more with correctly identifying seizure events compared to Run 9. The differences between the two runs could result from variations in hyperparameters, like learning rate, number of epochs, or batch size, the specific dataset splits used, or random initialization of the model weights. Implications for improvement. The results suggest that the configuration and hyperparameters used in Run 9 were more effective, and we might consider using similar settings or exploring variations around them to further optimize performance. Minimizing false negatives remains critical, and Run 9 shows better potential in this area, so future models could be fine-tuned based on its configuration to further reduce these errors. If any viewers have questions or thoughts about what might be contributing to these differences or want to discuss possible changes to the model setup, feel free to share in the chat. Given that the dataset remained the same for both runs, the differences in performance metrics likely stem from variations in the model settings rather than the data itself. Let's look closely at the model settings for each run to understand why these differences occurred. Analysis of model settings. Upon examining the settings, we can see the following similarities and differences. 1. Batch size. Both Run 9 and Run 10 used a batch size of 64. This setting controls the number of samples that are processed before the model's weights are updated. Since both runs have the same batch size, this parameter is not a contributing factor to the performance differences. 2. Epochs. Both runs were trained for 100 epochs. This is the number of complete passes through the training dataset. And since it is identical in both runs, it doesn't account for the difference in performance. Number 3. Initial learning rate. Both runs used the same initial learning rate of 0.001. The learning rate determines the size of the steps the model takes towards minimizing the loss function. Given that this setting is also the same, the learning rate does not explain the differences in accuracy and loss. 4. Data augmentation. In both runs, data augmentation was set to false. This means that no additional transformations, such as rotations, flips, or shifts, were applied to the training data to artificially increase its size and variability. Since this setting is the same, it does not contribute to the differences observed. 5. Shuffling. Shuffling was set to true for both runs, which means the data was shuffled before each epoch to help the model generalize better by reducing the likelihood of overfitting to the order of the training data. This identical setting does not explain the performance differences. Conclusion. Given that all the key model settings were the same across both runs, the differences in performance likely arose due to the stochastic nature of neural network training. Factors like the random initialization of model weights, slight differences in the order of data during shuffling, or the inherent randomness in the optimization process could all contribute to these variations. It's common for models, especially deep learning models, to exhibit some level of variability across different runs, even when the settings and data are kept constant. Engaging summary for the web page. Let's add a summary at the bottom of the web page to engage readers and invite them to think critically about the outcomes. Summary and reflections. As we've seen in this application, even when the data and model settings are kept the same, differences in performance can still occur between runs. This highlights an important aspect of working with neural networks. Sometimes, the process involves a bit of unpredictability. Small differences in the initial setup, like the random initialization of weights or the order in which data is processed, can lead to variations in results. But don't let that discourage you. This variability is a normal part of machine learning, and it can actually provide valuable insights. Each run teaches us something new about how our model behaves, what it excels at, and where there's room for improvement. We invite you to experiment further with different configurations or try out new data sets to see how these factors impact model performance. Have questions or thoughts on what might be causing these differences? Or perhaps you have suggestions on new settings or parameters to explore. Share them with us. We're excited to hear your ideas and engage in a discussion about how we can continue improving this tool together. Feel free to reach out or dive deeper into the dataset and the model by exploring the links and resources provided. Your curiosity and feedback are what drive this project forward. By providing this summary, we not only explain the results to our audience, but also encourage them to engage more deeply with the material, fostering a sense of collaboration and shared discovery. Model training performance. Comparing the last two runs. In our recent experiments with the EEG seizure detection model, we conducted two separate training runs using identical data sets and model configurations. Despite keeping the dataset and model parameters consistent, we observed some interesting differences in performance metrics between the two runs, which highlights the nuances and complexities inherent in training deep learning models. For both runs, we used a batch size of 64, which defines how many samples the model processes before updating its internal parameters. The number of epochs, or full training cycles through the entire dataset, was also kept constant at 100. Additionally, we set the initial learning rate to 0.001, a parameter that controls how much the model's weights are adjusted with respect to the loss gradient. No data augmentation was applied, meaning the model was trained solely on the original images without any artificial alterations or transformations, such as flips or rotations. Finally, we enabled shuffling for both runs, ensuring that the order of training samples was randomized each epoch to help the model generalize better. Despite these identical settings, we observed variations in the performance metrics. In Run 9, the model achieved a test accuracy of 96.67%, with an average training accuracy of 82.889% and an average validation accuracy of 90.04%. The corresponding training and validation losses were 0.4323 and 0.3520 respectively, indicating a relatively good fit with a low margin of error. Conversely, Run 10 showed a test accuracy of 90.00% with an average training accuracy of 73.06% and an average validation accuracy of 85.78%. The training and validation losses for this run were higher at 0.5729 and 0.519 respectively. This suggests that while the model still performed reasonably well, it did not generalize as effectively as in Run 9. These differences, while appearing significant, are actually a common occurrence in the field of machine learning. Neural networks, especially deep learning models, are influenced by various stochastic factors, such as the random initialization of weights or the random order of data presented during training. Even with identical settings, these random elements can cause slight variations in model performance. The lower test accuracy and higher losses in Run 10, for example, could be the result of less favorable initial conditions or subtle differences in how the model encountered the data during each epoch. Understanding these variations is crucial as it underscores the importance of running multiple experiments and not relying solely on a single run to judge a model's effectiveness. It also highlights the necessity of careful parameter tuning and the value of techniques like cross-validation to ensure that the model is genuinely learning patterns that are generalizable beyond the specific dataset it was trained on. Overall, these results remind us of the inherently probabilistic nature of machine learning. The key takeaway is to embrace the variability as part of the learning process, continually experimenting with different configurations and techniques to achieve the most robust and reliable outcomes. We encourage you to explore these concepts further by experimenting with different settings or data sets, and to share your findings or questions as you engage with this evolving tool. Your insights and feedback are invaluable to us, and together we can push the boundaries of what's possible in the realm of EEG seizure detection and beyond. Here's a suggested post to publish a link to your EEG seizure detection web application. New web application, EEG seizure detection. I'm excited to share our latest interactive web application that explores the power of deep learning in medical diagnostics. With this tool, you can dive into EEG spectrograms, analyze machine learning models, and understand how they detect seizures with high accuracy. What's inside? Visualize EEG data. See the differences between seizure and non-seizure EEG segments. Model performance metrics. Evaluate our deep learning models with accuracy, loss plots, and confusion matrices. Interactive experience. Select different runs, analyze misclassified images, and experiment with settings. Ready to explore the possibilities? Check it out now and let us know what you think. Explore the EEG seizure detection tool, BioniChaos.com/rhythmscan. Feel free to modify the post to better match your style or the specific platform you're posting on. This EEG seizure detection tool is a perfect embodiment of the mission and vision behind BioniChaos.com, where the aim is to bridge the gap between complex biomedical data and accessible, engaging tools for a wide audience. At its core, BioniChaos is about making the intricate world of biomedical science understandable and interactive for everyone, regardless of their technical background. This web application takes a crucial step in that direction by providing a hands-on experience with EEG data, allowing users to visualize and understand the complexities of seizure detection through the lens of machine learning. The tool offers an opportunity to explore how deep learning models work, how they can be trained, and how their performance can be evaluated in real time. By presenting data in an intuitive way, it demystifies advanced concepts such as convolutional neural networks, spectrogram analysis, and medical diagnostics. This aligns with the broader goal of BioniChaos, which is to promote learning and curiosity through interactive simulations, visualizations, and tools that bring scientific principles to life. Moreover, this application serves as a prime example of how BioniChaos.com integrates gamification and interactivity into scientific education. Users can engage directly with the models, experiment with different settings, and see how changes impact model accuracy and decision making. This interactivity not only makes the learning process more engaging, but also highlights the practical implications of data science in healthcare, reflecting BioniChaos' commitment to innovative, accessible education. Ultimately, the EEG seizure detection tool is more than just a web application. It's a gateway to understanding how data-driven technologies can revolutionize medical diagnostics. By inviting users to actively participate, experiment, and learn, it fulfills the mission of BioniChaos to create meaningful educational experiences that empower users to explore the frontiers of biomedical science and technology. If I were to ask the founder or developer of BioniChaos.com, I would be curious to learn more about the motivations and inspirations behind creating such an innovative platform. Here are some questions I might ask. 1. What inspired you to start BioniChaos.com, and how did you come up with the idea of combining biomedical data with gamification and interactivity? 2. How do you envision BioniChaos.com evolving in the future? Are there any new features or tools that you are particularly excited about developing or adding to the platform? 3. What challenges have you faced in making complex biomedical data and concepts accessible and engaging for a general audience? And how have you addressed these challenges? 4. How do you balance the need for scientific accuracy with the desire to create fun and engaging tools for your users? 5. Can you share more about the decision to focus on client-side processing and single-page applications? How do these choices align with the overall goals of BioniChaos.com? What role do you see AI playing in the future of BioniChaos, both in terms of content development and user interaction? 7. Given your experience with EEG and ECG data, are there other types of biomedical data or areas in biomedical science that you are particularly interested in exploring on the platform? 8. How do you see BioniChaos.com contributing to the broader conversation about healthcare innovation and the use of data science in medical diagnostics? 9. What kind of feedback have you received from users so far, and how has that feedback influenced the direction of the site? 10. Are there any collaborations or partnerships that you are looking to pursue to expand the reach or capabilities of BioniChaos.com? 11. What advice would you give to other developers or researchers looking to create educational tools or applications in the field of biomedical science? 12. How do you stay updated with the latest developments in both biomedical science and web technologies? And how do you integrate these advancements into your work on BioniChaos.com? Now 13. What has been the most rewarding part of developing and growing BioniChaos.com so far? And what keeps you motivated? These questions aim to explore the vision, challenges, and future direction of BioniChaos.com, while also providing insights into the thought processes and strategies that drive its development.